Hey, good looking people, it's Miss Heineman here. It is April 21st, and we are going to cover tangents to a circle. That's our focus today. So we're going to do a quick investigation here. I've drawn a tangent line for the circle below. The point of tangency is this point, is the point on the line that is also on the circle. So the point of tangency is on the tangent line and is also on the end of the radius here of the circle. So you're going to do this part. Use a straight edge to connect the center of the circle to its point of tangency, and then what do you notice about the relationship between the radius drawn to the point of tangency? So you can pause here, try it out, and then unpause and see what I see. All right, so if I draw the radius here, it kind of looks like these are perpendicular to each other, the radius and the point of tangency. And so that's actually true. All right. And so I'm going to write this like this. And that's the relationship. So in your yellow pages, we're going to put this picture in here. Okay, and write something with it. So radius to tangent line, because there are two relationships that we're going to look at. And this is for, and I was wrong before, this is for unit 11 circles, not unit 10. We already did unit 10. All right, so we're going to write a note here to ourselves just to remind ourselves. Oops, my pen. Okay, so the radius drawn to the point of tangency, just using this. Radius is drawn to the point of tangency, to a tangent line. Oops, let me just spread these out. Tangency to a tangent line creates right angles. They are perpendicular. Okay? So we're going to use that idea to cover the next two practice problems. So the first one I'll do with you. And if you need to pause to write this in your yellow pages, please do. But I'll do the first one with you, and then I'm going to have you pause, hopefully, and you can try the second one, and you can check with me. Okay? You zoom out a little bit here. So the relationship is that our tangent is perpendicular to the radius. So if I know where the point of tangency is, that's where the right angle is. So segment BC is tangent to circle A at point B. So here's my right angle. AC is 10, and the radius of the circle is 6. How long is AB? So we're going to make that X. All right, so Pythagorean theorem. Because I write a right triangle, x squared plus 36 equals 100. X squared equals 64. Take the square root of that and the positive number. X is 8. Okay, so we're looking at right triangles again. That's your goal. Tangent lines of a circle, you have Pythagorean theorem. All right, now I want you to pause. I invite you to pause and look at number 2 and see if you can figure it out. Where's your right triangle? And use that information to answer the question. All right, after you've tried number 2, we'll look here at our given segment BC is tangent to circle A at B. So here's my right angle at B. And I have a couple things going on. A is at 1927. B is at 1911, which tells us a couple things about the picture. It tells me that C, the coordinates of C, our final answer here, has to have a y-coordinate of 11. So hooray, we're part of the way there. And then we know AC is 34, and this distance here between 27 and 11, so the distance there is that they're 16 apart, means that AB is also 16. So there's 2 of the 3 sides of the right triangle. And if I find segment BC in this picture, then it'll help me find the x-coordinate of C. So I've got 16 squared plus x squared equals 34 squared. 256 plus x squared equals 1156. X squared equals 900. Take the square root. So x is 30. So in this picture, this length is 30. Now my x-coordinate is not just 30. Remember, this is a length, but look at my length. It starts at 19, and B is 30 away from C. So I have to move 30 to the right from 19. So my x-coordinate for C is actually 49. Okay, 19 plus 30, 49. All right, so that's one relationship. There's one more, and we're actually going to use a proof to show it. Okay, and so if we write a two-column proof here, we actually need triangles, so I'm going to draw this in. And when you draw a segment in, because you need it, you just write in your proof that you drew it. And the reason you can do that is because 2 points, any 2 points, determine a line or a line segment. So in this case, we're drawing a segment. So 2 points determine a line segment. So we have circle A. We have tangents. And remember, the segments that are tangent to the circle create right angles. So I've got right angles here. So I'm going to write that first. Segment TG is tangent to circle A at G. And segment TN is tangent to circle A at N. And those are both given. So the next thing we can write is that we know that there are right angles there at angle N and angle G. So angle N and angle G are right angles. Okay. The reason? Radius to tangent at point of tangency creates right angles. That's from part 1 of our lesson. Okay? Those right angles are super useful. So we've got one match there, right angles. So what else do we have? We have segment AT is congruent to itself. Reflexive property. And then we have the circle, right? Circle A. And what was good about having that circle there is that you can say the radii are congruent. Remember, if I'm moving too quickly, this is a video, so you can always play back or pause or whatever you need to do. So here's your reason. Review from last chapter, radii of a circle are congruent. And then we've got our 3 matches. So triangle TAG is congruent to triangle TAN by, and if I look at my picture here, looks like this. Just one of them. Right angle, hypotenuse, leg. I have RHL. Okay. And then you're just going to go back in your proof and make sure you showed all those. So I showed my right angles in step 4. I showed my hypotenuse was congruent in step 5. And I showed one of the legs was congruent in step 7. So then we can finish off our proof. If I can get a pen here. That TG is congruent to TN by CPCTC. Okay? So these tangents are congruent. That tangent and this tangent. Whoops. Something to notice here, what our proof tells us is that if the tangents start from the same point and go to the same circle, then they must be congruent. All right, so that is our second entry in our yellow pages. I call this the ice cream cone theorem. That's not its official name. It doesn't have like an official name. It has, just words. I like to call it the ice cream cone theorem because I think it looks like ice cream. So here you go. You have a circle. You have a point outside the circle, and you're going to draw your circle O. Two tangents from the same point on the outside. So what this tells us is that, oops, would like a different pen color. There we go. This proof tells us is if you start from the same point outside of the circle and draw two tangent lines to the same circle, they are congruent. So tangent drawn from the same exterior point to the same circle are congruent. That's all. The tangents drawn from the same point, so point T, the two tangents that are drawn here, TA, segment TA and segment TB are congruent. So we're going to use that idea for this next one. So Miss Brady put a point outside her circle. She drew two different tangents. Boom, they must be congruent. One segment was x squared plus 3. The other was 7x minus 9. The radius is 2x, oops, not 2x, x plus 2. Well, what I know is that the tangents are the same, so I'm going to set these expressions equal to each other. And I've got an x squared, so I'm going to move everything to the x squared side. So far I've got this, x squared minus 7x plus 3 equals negative 9. And then I'll move the 9 over, because I want that right-hand side to be equal to 0. So I can factor. All right, so two numbers that multiply to 12 but add to negative 7 are x minus 4, x minus 3. And using zero product property, you've got x minus 4 equals 0. Oops. And then x minus 3 equals 0. X equals 3. X equals 4. Let's see what the question's asking. Find the smallest value of x. Ooh, okay, so I'm going to pick x equals 3. How far is her point from the center of her circle? Sorry about that. My computer is being funny. So we want this distance. Okay, so I know these two. I've got my ice cream cone theorem here. I know I've got right angles. So I can deal with the right triangles. And if I plug in 3, I know this radius is 5. This side is 7 times 3, 21 minus 9. This is 12. This should be 12 also. And I want to figure out this segment. So I'm going to look at this triangle. 5, 12. And then this one. So 5 squared plus 12 squared equals question mark squared. So 25 plus 144 equals question mark squared. 169 equals question mark squared, and I'll take the square root of that. So question mark is 13. So how far is her point from the center of her circle? 13. And the smallest value of x was 3. There's your lesson today. And if you have any questions, just meet me at our Zoom office hour tomorrow at 11. I hope you're doing well. Miss you. Bye.